This is what the Sun might do to Earth in 2025. On March 13, 1989, planet Earth was attacked from space. A catastrophic event occurred that left millions of people without power and resulted in extensive damage. While one might assume that this was the result of an unnoticed alien attack, the truth is far more plausible: a solar storm. The effects of this solar storm were particularly devastating in Quebec, where an estimated 6 million people were left powerless. Imagine waking up to a cold home, businesses and schools shuttered, and even the bustling Montreal Metro having to halt its operations during morning rush hour. To make matters worse, the airport was also forced to close its doors. The impact was truly immense. This solar storm unfolded during a period known as Solar Cycle 22, characterized by heightened solar activity. These cycles occur approximately every 11 years, and scientists predict that a similar event to what transpired in Quebec could potentially happen again by 2025. But don't worry, as you will see at the end of this video, every medal has two sides. Keep watching the video to get to know more about it. The importance of the Sun. In the grand tapestry of the cosmos, the Sun holds an unparalleled significance for our planet Earth. It stands as the radiant centerpiece, the beacon of life, and the architect of Earth's rhythms. Its influence transcends the boundaries of the celestial realm, permeating every facet of our existence. In this video, we shall embark on a journey to uncover the profound importance of the Sun, delving into its multifaceted roles that shape the very existence of life on our blue-green orb. At the heart of the Sun's paramount importance is its role as the ultimate source of energy for life on Earth. Through the process of nuclear fusion, the Sun emits a ceaseless torrent of light and heat, illuminating the cosmos and bathing our planet in life-sustaining radiation. This energy is harnessed by Earth's biosphere, initiating a cascade of processes that drive photosynthesis, the bedrock of terrestrial life. Photosynthesis, orchestrated by an intricate array of plant life, transforms sunlight into chemical energy, breathing life into Earth's ecosystems. It is this process that endows our planet with the oxygen we breathe and the sustenance we consume. In essence, the Sun is the cosmic engine that fuels the cycle of life on Earth, supporting an intricate web of interdependent organisms. Beyond its role as an energy bestower, the Sun is Earth's master orchestrator, weaving the fabric of climates and seasons. Its rays, striking at various angles throughout the year, govern the ebb and flow of temperature and weather patterns. The tilt of Earth's axis relative to its orbit around the Sun bequeaths us with the symphony of seasons: spring's awakening, summer's warmth, autumn's harvest, and winter's reprieve. These seasonal shifts sculpt the landscapes and habitats that cradle life. They dictate the migratory patterns of countless species, influence the behavior of flora and fauna, and guide the life cycles of numerous organisms. Moreover, the Sun's radiant energy drives the water cycle, a fundamental force that sustains the delicate balance of Earth's ecosystems. Astrophysics of the Sun. The Sun has long captivated scientists with its enigmatic nature, driving astrophysicists to unravel its mysteries and gain a deeper understanding of its intricate life cycle. Over the course of decades of exploration and discovery, we have unearthed important insights into the Sun's composition and structure. Similar to other stars, the Sun is an immense sphere composed primarily of hydrogen and helium. With a diameter of 1.4 million kilometers, it is a staggering 109 times larger than Earth. However, despite its vast size, the Sun is 4 times less dense than our planet due to its unique composition. Contrary to popular belief, the Sun is not simply a mass of glowing gas observable through a telescope. Like Earth, it possesses distinct layers with varying temperatures, each boasting its own unique characteristics. To better understand the Sun's structure, it can be envisioned as a colossal onion, with the core situated at its center and subsequent layers superimposed upon one another. The core is the primary source of the Sun's energy, sporting an exceptionally high temperature and immense density resulting from intense pressure. These conditions provide the ideal environment for nuclear reactions to occur. Through the fusion of hydrogen, the Sun predominantly produces helium. However, due to the extreme temperatures and pressures within the core, secondary nuclear reactions generate trace amounts of heavier elements like carbon, oxygen, and nitrogen. Temperatures within the core can reach an astonishing 15 million degrees Celsius. The energy produced within the core must then be transported to the surrounding regions. This is achieved through radiative transport, wherein energy in the form of radiation interacts with particles in the surrounding environment. Some atoms within the radiation zone can withstand these conditions, absorbing and storing energy before releasing it as new radiation. This facilitates the transfer of energy from one atom to another as it makes its way through the radiation zone. Temperatures within the radiation zone range from 7 million to 2 million degrees Celsius. Once the energy exits the radiation zone, a new transport mechanism is required to convey it to the sun's surface. Outside of the radiation zone, temperatures are relatively cool, making it easier for atoms to absorb energy. However, these atoms do not readily release energy as their surroundings are cool and dense. Consequently, the energy transfer through radiation diminishes significantly. Instead, the energy is carried through the convection zone. Atoms absorb heat and rise through this zone, eventually transporting the energy to the sun's visible surface, known as the photosphere. The temperature in the convective zone decreases further, reaching about 2 million to 6,000 degrees Celsius, 3.6 million to 10,800 degrees Fahrenheit, as you move outward from the radiative zone towards the sun's visible surface, known as the photosphere. The sun is ever-changing. The photosphere, the visible surface of the sun, serves as our gateway to the wonders of our star. It is through this unique window that photons generated in the sun's core escape and journey across the universe, ultimately reaching our eyes. These particles of light, which have traversed the depths of space for longer than we can comprehend, greet us whenever we gaze upon the sun. The photosphere, therefore, is not merely a part of the sun, but a conduit that connects us to its majesty. However, accessing the photosphere was not always feasible for early astronomers. Their rudimentary telescopes, ill-equipped for studying the sun's astrophysics, were hindered by their blinding brilliance. Attempting to observe the sun directly would have resulted in irreparable damage to their eyes. Yet as time passed, astronomers discovered a solution: specialized filters that enhance the observability of the sun. Through these filters, they were able to discern the presence of granules on the photosphere, resembling a pot of boiling water dotted with tiny, moving bubbles. Astonishingly, each of these granules measure about 1,000 kilometers wide, dwarfing our own planet. Intriguingly, these luminous granules were often accompanied by a contrasting phenomenon known as sunspots. These dark spots emerge due to the influence of powerful magnets beneath the sun's surface. They appear cooler and darker compared to their surroundings, drawing the attention of astronomers. Like clockwork, the cycle of bright granules gives way to the enigmatic appearance of sunspots. In a nutshell, sunspots form when magnetic field lines below the surface poke through the sun's photosphere. Occasionally, the sun, perhaps feeling particularly exuberant, treats us to extraordinary displays of solar flares and prominences. Solar flares akin to splendid fireworks composed of minuscule particles embellish the sun with vibrant hues, emitting a special form of light. Prominences, on the other hand, manifest as mesmerizing loops of fire that elegantly dance above the sun's surface, reminiscent of a celestial crown adorning our star. And then there are faculae, the radiant patches that punctuate the photosphere. These areas, characterized by intense magnetic activity, emit a brilliant glow that distinguishes them from the rest of the sun's surface. Indeed, the photosphere is a bustling stage, teeming with movement and captivating surprises. It is here that the sun orchestrates a grand performance for us, a spectacle that reminds us of its boundless wonders and tantalizing mysteries. However, if you happen to point your telescope at the sun at random times, you might not be able to see anything. In other words, there are periods where the sun's photosphere is almost devoid of any feature, and others where it is enriched with them. Astronomers long wondered and studied this phenomenon, and they have come to the conclusion that the sun undergoes cycles: solar minimum and maximum. Indeed, our radiant celestial neighbor is far from static. For example, sunspots wax and wane every now and then, and so does the magnetic field by literally flipping its orientation over the course of 22 years. The first cycle regarding the sunspots is the Schwabe cycle, named after the Swiss astronomer Samuel Heinrich Schwabe. It spans approximately 11 years, and it is characterized by the waxing and waning of sunspots on the sun's surface. At the cycle's maximum, sunspots are abundant, creating dark spots on the sun. As the cycle progresses to its minimum, sunspots become less frequent. Schwabe cycles are repetitive yet difficult to predict. A cycle can be as short as 8 years or as long as 14 years and varies dramatically in intensity. The current cycle, solar cycle 25, began in December of 2019. Solar activity is expected to ramp up until the predicted solar maximum between 2024 and 2025. The second cycle, on the other hand, is known as the Hale cycle, and it takes twice as long as the Schwabe cycle to occur. What makes the Hale cycle particularly intriguing is its focus on magnetic polarity. Over the course of this cycle, the sun's magnetic field flips, the north magnetic pole becoming the south magnetic pole and vice versa. Picture this. At the beginning of a Hale cycle, the magnetic field lines emerge from the sun's northern hemisphere. By the cycle's end, they reverse, emanating from the southern hemisphere. In other words, the Hale cycle is made up of two Schwabe cycles with two different polarizations. The polarization reversal is a very common process in the universe. Earth's magnetic poles also flip, but the interval between the reversals is much longer, averaging about every 300,000. The last pole reversal happened about 780,000 years ago. Last but not least, the Gliesberg cycle is a more extended cycle, with a period of about 88 years that concerns the amplitude of the sunspot activity over time. While not as pronounced as the Schwabe or Hale cycles, the Gliesberg cycle hints at more complex long-term variations in solar activity. Researchers believe that this cycle may be influenced by interactions within the sun's interior, but research is still ongoing. Solar cycle driver. And of all the cycles that have been studied, the Schwabe cycle stands out as the most fundamental and captivating. It raises some important questions that have led researchers to delve deeper into the forces that drive it and the reason behind its 11-year duration. To comprehend what propels this cycle, it is crucial to understand the definition and origins of it. The first person to provide a definition for this cycle was Schwabe himself. He meticulously observed the sun from 1826 to 1843 and made a groundbreaking discovery. The sun rotates on its axis once every 27 days. Furthermore, he discerned that the sun's activity experiences a cyclic pattern over the course of approximately 11 years. Schwabe's theory was primarily based on the emergence and disappearance of sunspots, which are known to be created by the sun's magnetic field. Consequently, it can be understood that the primary driving force of the Schwabe cycle is indeed the sun's magnetic field. The cycle experiences a period of rise from minimum to maximum phase, which typically spans around 4 years, followed by a subsequent decrease from maximum back to the minimum that spans approximately 7 years. Another significant observation made by Schwabe was that the sun's activity has a direct impact on Earth. The solar cycle induces variations in our planet's magnetic field. During the solar maximum, characterized by an abundance of sunspots, solar flares and coronal mass ejections, CMEs, explosive releases of charged particles from the sun's surface, terrestrial effects become more pronounced. An event of this nature occurred on March 13, 1989, when a colossal CME caused a major blackout in Quebec. This incident highlighted the profound influence of energetic particles carried by the solar wind on our weather patterns and the potential for disruption to communication, navigation, and power systems. Presently, it appears that we are on the brink of a new solar maximum. This implies that we can expect a surge in sunspot activity, an abundance of coronal mass ejections, and an overall increase in the sun's unpredictability. While this may be exciting for scientists studying the sun, it poses a significant risk to our satellites and telecommunication systems, which could be compromised by the intense and unpredictable solar activity. This could start soon, and it would have probably reached its peak by 2025. Consequences. I'm just going to guide you through 2 of the consequences of a possible solar storm happening in 2025. First of all, it could interfere with your mobile devices. Perhaps you won't be able to use your phone for a whole day. Perhaps that will be an occasion for us to gather and experience how life was before the advent of social media. But how does this work exactly? Well, during a solar storm, the Earth's magnetic field is disturbed by a surge of charged particles from the sun. This can induce electrical currents in conducive systems on Earth, including power lines, pipelines, and even long metallic structures like railways. Mobile phones, especially those in areas with weaker signal strength or in regions close to power lines, may experience interference or disruption in service. This interference can manifest as dropped calls, static on the line, or even difficulty in establishing connections. Additionally, electronic circuits in mobile phones can be affected by the increased level of electromagnetic radiation during a solar storm. This might result in temporary malfunctions or reduced performance. But every medal has two sides. Hear me out. There will be no better time for you to experience amazing auroras during the solar maximum. Why, do you ask? Well, this is quite easy to explain. Auroras occur when charged particles from the sun collide with gases in Earth's atmosphere, such as nitrogen and oxygen. These collisions release energy in the form of colorful light. During a strong solar storm, auroras can be visible at lower latitudes than usual, sometimes even in regions where they are not typically seen. This means that people at lower latitudes who don't often get the chance to witness auroras may have the rare opportunity to see these beautiful natural displays.